Okay, can I start?
Yes. Okay, we continue our conference, and our next speaker is Sergey Antonyan. Let's go.
Okay, thank you. Good morning, everybody. First of all, I would like to thank you for organizing such an online conference. I thank to Taras Banach for arranging, for participating in correction of time of my talk. And I am sorry for not showing up yesterday, because I had some technical problems, not like today, more serious. So I'm going to speak about Gromov-Hausdorff hyperspaces. Let me start recalling you the definition of a Hausdorff distance between two subsets of a metric space, MD. Here you see the formula. So we have to measure the distance from a point A of the set A to the set B, and then compare this number with the similar number distances from B to A and take the maximum. This is the Hausdorff distance between two subsets. When we consider the non-empty compact subsets of M, and we denote by 2 to the M, this set, then Hausdorff distance is a metric on this set, and it is called Hausdorff, it is called the hyperspace of M. So 2 to the M is called hyperspace of M. So this idea was used by Mikhail Gromov to introduce distance between two metric spaces, two compact metric spaces. The idea is quite similar and simple. He embeds isometrically X and Y by means of isometries here, I from X to M and J from Y to M are isometric embeddings. And then Ix and Jy become as subsets, compact subsets of the same metric space. And then we can measure Hausdorff distance between them. I am sorry, there is no space here. You cannot see everything, but okay. Then we take the infimum of all of these distances when over all possible isometric embeddings, I and J, and also M is varying. So the infimum of all possible these distances is called the Gromov-Hausdorff distance between X and Y. Another way, maybe more pleasant to see this number is the following: fix two metric spaces, X and Y, with the metrics, and denote by D the set of all possible metrics on the disjoint union, X plus Y, and then extend the metrics D sub X and D sub Y to this disjoint union. So this extension exists, and of course is not unique. And then we take all possible extensions and measure the distances between X and Y with respect of D. Now we take the infimum of these numbers when D is varying over this set, or all possible extensions of the matrix D and C. So this is again the same number the Gromov-Hausdorff distance. Okay, here are some well-known properties. Now, Gromov-Hausdorff distance becomes, evidently this is a zero if X and Y are isometric compact metric spaces. That's why if we want to obtain a real metric, we have to consider the isometric classes of these compact metric spaces. So by GH, we denote the set of all classes, isometric classes. On this set, the Gromov-Hausdorff distance introduces a metric for which we use the same denotation, D sub GH, and it is called Gromov-Hausdorff space. Okay, let me skip this. And let me recall you the notion of Urysohn universal metric space. In 1925, Paul Urysohn proved the following remarkable result. He proved that there exists up to isometry unique metric space U satisfying the following properties. First, U is Polish. In topology, it means that it is a separable and complete metric space. U contains an isometric copy of every separable metric space. And U is a so-called ultra-homogeneous, which means that given any isometry between two finite subspaces of U, this isometry extends to an isometry of the whole space U. So such a space exists, and it is now called Urysohn universal metric space. So the Urysohn space was introduced by Urysohn, as I said, shortly before his tragic death in 1924, and his results were prepared for publication by his friend, Pavel Alexandrov, and published posthumously in short form in 25 and with details in 27. After Urysohn result was published, Stefan Banach and Stanislav Mazur proved that the space of continuous functions on the interval 0, 1 is universal for all separable metric spaces, universal in the sense I mentioned above. But this space is not ultra-homogeneous. Dually, the separable Hilbert space L2 is ultra-homogeneous, but it is not universal. And there is an open problem of Alexandrov to find an explicit model for Urysohn space like C01 or L2, but these two candidates, they don't satisfy. So this problem still remains open. Okay, here is some story. Now let's go ahead. Another remarkable result was discovered by Georgian mathematician Khukhunashvili in 1955, who proved that Urysohn universal metric space U satisfies the following property. So just the same property in the Urysohn theorem where A and B were finite subsets. Here, he proved that the same holds true when A and B are isometric compact subsets of U. Then any isometry can be extended to an isometry of the whole space. So this is a very nice result, and this is very workable. So since 20 years, Urysohn universal metric space is actively studied. Now already 25 years, maybe I should to say. And then, for example, I'm not going to use these results, but let me recall you that the topological structure of U is known. It is homeomorphic to the Hilbert space. Homeomorphic, not isomorphic. Denote by iso U the group of isometries endowed with the pointwise convergence topology. It is also a Polish space, this group. And this space, the group space, is also known to be homeomorphic to L2. This is a result of French mathematician Malary. And another good result is by Cameron and Vershik, that the group, so this is a huge group. This is not, of course, not locally compact, not Lie, but this is a monothetic in the sense that there is an element generating a dense subgroup of U. This was proved by Cameron and Vershik. So the next theorem, this belongs to Berestovsky and Vershik. Surprisingly, Gromov at that time had no idea about the existence of Urysohn space. And Berestovsky and Vershik proved this because they knew about the existence of Urysohn space, and they proved that in the definition of Gromov, it is sufficient to consider only one space, U, and then consider all isometric embeddings of X and Y into this space, and again take the infimum of all these distances, Hausdorff distances, then we will get the Gromov-Hausdorff distance, the same. So in the second edition of Gromov's book already appeared this definition, and he absorbed that the Gromov-Hausdorff space is nothing more than the orbit space of the hyperspace of the Urysohn space. So you remember, if we have here a metric space U in this case, then 2 to the U is the hyperspace of all compact subsets of U. And iso U is the group of isometries. The group of isometries naturally acts on this space. Then we take the orbit space with the quotient topology. It turns out the Gromov-Hausdorff space is just this orbit space. Okay, I have to go faster because it's a challenging open problem to describe topological structure of this space. This talk is towards this problem. Okay, in this talk, I am considering the Gromov-Hausdorff hyperspace of a given Euclidean space. By definition, this consists of all those classes of compact metric spaces, which are isometrically embeddable into the Euclidean space Rn. By Rn, we mean the standard Euclidean space with the metric square root and so on. So again, GHRn consists of all those classes which have a representative as a metric subspace of a Euclidean space. It turns out that we can consider, like in Berestovsky-Vershik theorem, consider the infimum of these numbers. Consider all possible embeddings of X and Y into the given Euclidean space and take the infimum and call this number temporally Euclidean Hausdorff distance. Okay, Euclidean Hausdorff distance. So my idea is to present the structure results about this Gromov-Hausdorff hyperspace of Rn. Okay, let me recall you. We see above some notions of homogeneity, ultra-homogeneity, homogeneity, and so on, but it turns out the most homogeneous space over the world is the Euclidean space in the following sense. In a Euclidean space, even we have arbitrary two isometric subsets, not necessarily finite or compact, any two isometric subsets, then every isometry between them can be extended to the isometry of the whole space. This is a well-known result in linear algebra too. It is not contained in every textbook. Okay. So we consider the isometry group of the Euclidean space. Then this isometry group naturally acts to the hyperspace of the Euclidean space. And similarly, we can consider the orbit space under this action of the hyperspace of Rn. And then I proved that, okay. And we proved that, in fact, this number, the distance between a given x to the orbit of y, orbit under the action of this isometry group, is the same as the Euclidean Hausdorff distance. Now, comparing the Gromov-Hausdorff and Euclidean Hausdorff, it is evident this inequality, and this inequality, so the equality cannot be attained, in fact. So it is well known, a simple example. If X is a 3-point space, the vertex is an equilateral triangle, and Y is a singleton, then the Euclidean Hausdorff is square root over 3, and the Gromov-Hausdorff is 1/2, then you see the strong inequality here. So our first result is that the Gromov-Hausdorff of the Euclidean space is in fact homeomorphic to the to this orbit space. So again, the hyperspace of Rn, and factorizing under the action of the group of isometries of Rn. And I think so here there are some details. Maybe, no, let me sketch briefly. We consider inside of the hyperspace of Urysohn space those elements which are embeddable isometrically, embeddable into the Euclidean space, and then define the function f from here to here to Gromov-Hausdorff Rn by this formula. We send A to the isometric class of JA, where J is an isometric embedding. So we understand that the isometric embedding is not unique. And then without these brackets, the definition would be not correct, but we have the brackets, which mean the isometric class. And Chuchunashvili theorem helps to prove that this definition is, the F is well-defined. So J is not uniquely defined, but its isometric class is uniquely defined. So then we have this map F, and then it is easy to see that this map F is constant on the orbits on Rn. On Rn, the isometry group is acting. So F is constant on the orbits, and then it gives rise to a continuous map from this orbit space to the Gromov-Hausdorff of a Euclidean space, and just this map is the desired homeomorphism, which is claimed in the theorem. Okay. For the homeomorphism, one part is trivial. From this inequality, it follows that F tilde is continuous, even uniformly continuous. The continuity of the inverse map is not trivial, but it is a fact. So, well, this is what is claiming in the theorem. Sorry. Okay. So we have this. Okay. Now let's go ahead. The action of the isometric group, the natural action here, is proper in the following sense. In this case, since this hyperspace is locally compact, I'm giving here an equivalent form. Proper means that if we take any compact subset, then this set in the group, which is called the transporter from K to K, consisting of all those elements such that GK intersects K, has compact closure. So proper actions introduced by Richard Palais were invented to generalize the theory of compact group actions to the case of non-compact, to the case of the actions of non-compact groups. As in the compact case, we have the following nice properties. Every stabilizer under a proper action is compact, and every orbit is closed and is homeomorphic to the quotient space, this. Okay. A classical result by Van Danzig and van der Verden gives an interesting examples of proper actions if XD is any connected locally compact metric space, and G is the group of isometries with a compact open topology, then the G is a locally compact group. And in the case of manifolds, this is a Lie group. And the natural action given by evaluation is a proper action. So here we have a particular case. To the properness of this action, we can prove without making a reference to Van Danzig and van der Verden, but it is interesting to mention this result. Proper actions are interesting because they permit the so-called existence of so-called global slices. For a locally compact group G and its subgroup H, a subset of a G space X is called H slice if the following holds. Maybe I have a picture here. Okay. So S is H invariant, also means a smaller group is acting on S. S is closed in the whole space. So two translations of S are disjoint. Otherwise, G should be an element of H, in which case GS is just coincide with S. And the saturation of S is the whole space. So Abels proved that if we have a global slice, the existence of global slices is interesting because the studying of orbit spaces, which is our case, remember, is homeomorphic to the orbit space of S under the action of the smaller subgroup. So here is the situation. We are interested to study the orbit space of the bigger space. But Abel's theorem says that this is homeomorphic to the, or if we consider only S on which a compact group H is acting. And these two orbit spaces are homeomorphic. Thus, the studying of this orbit space is reducing to the case of when the acting group is compact. In our case, X is the hyperspace of Rn. The locally compact group, so the Lie group, is the isometric group of Rn, and the K is the maximal subgroup of G. And then by this result, we have this homeomorphism. So remember, we are interested to find the topological structure of this one. So by Abel's result, this is homeomorphic to this one, where S is an ON global slice of this hyperspace. From here on, where we will show a convenient global slice, otherwise it is difficult to work with this hyperspace because we don't know what is S in general. But in our problem, we can find what is S. Here some geometry is very helpful. A classical result of Chebyshev claims that if we have any compact subset of Rn, then there is a unique closed ball called Chebyshev ball of A, such that A is contained in CH. Sorry, unique closed least ball with the least radius, with the smallest radius, which is called the Chebyshev ball, such that contains A, like in this picture. Okay, its center is called Chebyshev center. The radius is called Chebyshev radius. It is evident that Chebyshev center map is equivariant under the action of the isometric group. And the preimage of the origin under this map is just the global ON slice for 2 to the Rn, which is present in Abel's theorem. So in other words, T of Rn are all subsets of Rn whose Chebyshev center is the origin. So since it is a global slice, then Gromov-Hausdorff Rn is homeomorphic to this orbit space. So in this step, we reduce the problem to the action of a compact group, ON. So working with compact Lie groups is more pleasant and some theory exists. Now, how to compute this orbit space? We denote by Chebyshev n all subsets of Rn whose Chebyshev ball coincides with the unit Euclidean ball. Okay, we consider all those A for which this fixed ball is Chebyshev ball, the least volume ball which contains these sets. Okay, so this studying this hyperspace is crucial here. So we proved that the TRN is equivariantly homeomorphic to the open cone over Chebyshev n. This equivariant homeomorphism induces a usual homeomorphism between orbit spaces. Let me recall you that the open cone is like the ordinary cone, but the generates are infinite rays. So this is the open cone. The proof is very easy, and maybe I don't have much time. I have to. How many minutes I have? I'm sorry.
10 minutes.
Oh, then there is time. Then I will recall you what means equivariant absolute retract. Equivariant absolute retract is a space X which satisfies the property of Urysohn-Titze extension theorem, but in the category of G spaces. So we have a metric G space here. It's closed invariant subset A, then every equivariant map extends to an equivariant map. In our case, so G will be the orthogonal group. So the theorem, in the theorem, we see several properties that the Chebyshev hyperspace is ON equivariantly contractible to its fixed point Bn. So this is easy. Chebyshev hyperspace is ON equivariant neighborhood retract of this. And in a final stage, this is interesting that the Chebyshev hyperspace is ON equivariant absolute retract in the sense of the above definition. Maybe I will not stop on the proofs, on the ideas of the proof. So the most difficulty is the last one. And after that, when we establish the last property, that the Chebyshev hyperspace is equivariant absolute retract, then we get that the orbit space of that is an ordinary absolute retract. Here we use the following general result known from 88, that if we have a equivariant absolute retract, then always the orbit space is an absolute retract when the acting group is a compact group. So from this, combining this result and the above result, we get this fundamental property of this orbit space. So now our goal is we are going to prove that in the final stage, this orbit space will be homeomorphic to the Hilbert cube. One of the ingredients of the Hilbert cube is to be absolute retract, compact. Of course, these spaces are compact, I didn't say, but okay. Okay, just in the next theorem, we claim that the Chebyshev hyperspace is homeomorphic to the Hilbert cube, which by definition is the countable power of the 0-1 closed interval. And also its orbit space is homeomorphic to the Hilbert cube. And then this implies that our hyperspace, our orbit space of the hyperspace, which is just the Gromov-Hausdorff hyperspace of Rn, is homeomorphic to the punctured Hilbert cube. Punctured Hilbert cube, I mean the complement of a point in the Hilbert cube. As it is well known, Hilbert cube is homogeneous space. It means doesn't matter which point we remove, the remaining space is topologically the same. So this is our probably main result, which claims that the Gromov-Hausdorff hyperspace of Rn is homeomorphic to the punctured Hilbert cube. So here just one line about the proof. As we have shown, this orbit space is homeomorphic to the open cone over the orbit space of the Chebyshev hyperspace. And then using this one, we get that this is open cone over the Hilbert cube. But it is well known by a result of Chapman, classical result of Chapman, that the open cone over the Hilbert cube is homeomorphic to the punctured Hilbert cube with a removed point. So in fact, here, my talk, because I have no more results here, are some arguments how to prove that it is a Hilbert cube, but in this case, the idea does not say many things. So by Theoretic's theorem, Hilbert cube has two ingredients. It is the being compact, absolute retract, and the second one is satisfying the so-called disjoint disks property. Absolute retract we already have established, and then next result is a next step would be verifying this one, but this is a long issue, and I'm not going to stop here. Okay, so these two theorems are playing important role in proving that in identifying Hilbert cubes. Okay, here are some details. I will miss them, skip them, and let me end by showing you some literature, and this is the end. Thank you for your attention.